Hi all, I'm Mahima Mathews and I'm from Kerala, India. And I'm so happy to be talking to you all today. And thank you, Terrell, actually, for this wonderful opportunity. And myself, I'm a PhD student at IIIT Kottayam, and I also work as an assistant professor at Cochin University, again in Kerala. And as Terrell have just now told, I'm also part of the quantum cryptography team from Quantum Computing India. That's the brief about me. And I look forward for this opportunity as a lot of collaboration or like in invites or something like that. So hopefully, so this is where I work and yeah. So let's get into the post-quantum cryptography and what it is and all. So when we start with post-quantum cryptography, definitely we have to talk about the classical cryptography that we have today. So classical cryptographic systems are basically the symmetric encryption and the asymmetric encryption. So I believe this is all familiar, but still I'll just go through for a recap. So both these systems rely on something as keys. Like if the key is broken, then almost all these systems are like of no use. Like however complexity or however computational power, complexity, whatever effort you take in, if the key is broken, then this system is in of no use. So again, we have other schemes like digital signature and hashing for various purposes, like for ensuring the data is right and no non-repudiation uses, etc. Now, the problem that we are going to be in is that our cryptographic systems that basically use symmetric encryption today use pseudo-random generators. So pseudo-random generators means that we definitely need a random number, but they are generated using some sort of algorithm. So the problem with that is best explained using a slot machine. So these slot machines are actually expected to generate random numbers, but they have some algorithm that benefits the owner of the slot machine. So what happened is in one of the casinos where the slot machines was placed, certain people continuously monitored these slot machines, and based on the outputs it generated, they were able to actually back engineer and like what should I say? They were able to regenerate the algorithm and predict what is the next possible outcome. So what is the problem with pseudo random generators are they have some sort of hidden pattern in them, however random we build it. So these hidden patterns could be identified and actually can result in breaking the symmetric encryptions that we have today. Now we have the asymmetric encryptions. Asymmetric encryption schemes are based on some hardness of a mathematical problem. So for example, we have our RSA algorithm. RSA algorithm is relying on the hardness of prime factorization. So if you have a number n, which is actually a product of two prime numbers, when the number is n, when the number n is very huge or p and q is very huge, you cannot design or you cannot have an algorithm in a classical system which actually solves in within the usable time. When it is a 2048 bit number, we have a overhead of around 10 million years and all to actually solve this. So we are pretty much safe. Now, what is the problem right now? Why we are talking about all this right now is because of the quantum computers. Now, what quantum computers can do is we had pseudo-random generators in the symmetric section and the mathematical problem-based asymmetric section. Now, what is the problem? We have quantum computers which can actually find the hidden patterns in the numbers or the values, and also can actually solve the basic mathematical problem that we rely on today, that is the prime factorization using Cho's algorithm, etc. And we have other methods also coming in which can actually solve them using the quantum annealing, etc. So right now, the advancements in the quantum computing area, which is actually resulting in very efficient algorithms that can solve algorithms which was not solvable till now. That is a very good thing, but it is actually affecting cryptographic systems that we have today. So one good thing that we are actually able to solve new algorithms, that is a very good thing, but it affected in a different sector, that is our cryptography. So now when do we need to worry? Okay, so when our time, so if we need to store this particular data that we have for 10 years, okay, now if quantum computers is expected to come in, or the algorithm that we use to store that data will be broken by a quantum computer, and the quantum computer will come in like 5 years, then we are in danger. So we have to shift on. So if that is what like we have to have a good idea, like that is why it is the right time. Towards the end we will clearly analyze why this is the right time to actually have a shift. So a cause of concern appears if this particular proportion is not met. Okay. Now, what is actually quantum safe cryptography? So we told we have classical systems that we have today, and which was very well protected by the classical schemes that we have. But with the quantum computers coming in, apart from the classical attacks that we already had, we also have now quantum attacks. So we have two attacks now to deal with, that is the classical attacks and the quantum attacks. So now how can we secure our systems when the quantum computers are also going to coexist? So we basically have three methods. One is entirely quantum cryptographic system. This is actually a long way ahead. So to start with, we have the QRNG schemes. That is for solving the pseudo random numbers, we can basically replace them with the QRNG numbers. That is the quantum random number generators. So it is actually a good solution for the pseudo randomness, because this will give actually a physics based, quantum mechanics based random numbers, which is actually a very good solution because they do not have a hidden pattern in them. So that is actually a good solution, but pure quantum encryptions are yet to be developed. So hopefully we can see such algorithms in the future. Next approach is combining the architecture of the classical systems and the quantum. So that is actually QKD systems. So when we talk about quantum cryptography, what we hear is QKD. So quantum key distribution is actually like where we are using RSA. RSA is basically being used for key exchange, right? So there we can actually maybe replace or enhance it using the QKD system. So what QKD system helps us is, it is actually giving us a method to exchange the key. It is not actually encrypting the message. We have to again encrypt the message based on some of the classical systems, classical encryptions that we already have. So that is why it is called a combined architecture of classical and the quantum. Now we have the post-quantum cryptography. It is similar to what classical, how it works today, but we are actually choosing problems. Like RSA. RSA is actually a problem that was not solvable. RSA is based on a problem that was not solvable by a classical computer. Now we are going to choose problems that is not solvable by a quantum computers. So actually post-quantum cryptography is similar implementation. It has nothing to do with quantum mechanics principles. It is actually problems that are hard for quantum computers, and the example is lattice-based, code-based, etc. that we are going to see in detail today. So I hope the background of these cryptographic systems is clear. So if you have any questions, can I move on?
You can. I think a lot of people, this is one of the reasons I wanted to bring you, and I'm not saying our community is like that, but a lot of people in general think that post-quantum cryptography is the quantum aspect of it, but it actually has nothing to do with quantum, at least
Yes,
as NIST is doing it.
Yes. So purely like when we talk about the quantum, it is based on physics principles. Like post-quantum cryptography, it has nothing to do with exactly how the physics principles and quantum mechanics work. It is similar to what we have today. Those algorithms, what we have today, but the difference is that they rely on problems that is not solvable by a quantum computer. Like they are mathematically proven, like that is what we see in like some of the problems which are actually currently theoretically considered that it is not solvable by a quantum computer. People like Shor and all could bring in actually algorithms to solve them. Until then, they are considered to be secure. That is the only thing we can say. Until actually we have an effective algorithm to actually solve those problems, we can say post-quantum cryptography is resistant to a quantum attack. So that is how it works. Okay, can I proceed? Okay. So now post-quantum cryptographic approaches, basically we can do in two ways. One is we can take existing scheme, that is a simple method is take RSA itself, complicate it. Take a SHA, complicate it. Like if it is a SHA-2 algorithm, actually increase the bit size. That is a simple approach of post-quantum cryptography. Like make it difficult for the quantum computers. That is the simple approach of post-quantum cryptography. So the first basic approach is modification in existing schemes. We had a modified RSA algorithm in the competition sort of consideration as well, but it failed because it takes almost like days to generate the key. So that is not very efficient in the implementation side. So when we go to the implementation side, they have these increasing the complexity of the existing schemes have limitations. So the next approach is bring in other families of solutions or the problems which are considered to be quantum safe now. So that is why we are actually talking about these approaches. These are families of algorithms that are actually considered to be quantum safe. So this term considered is very important. As of now, they are considered to be quantum safe. So it keeps evolving. So these are the basic two approaches. These two approaches are there. For example, hashing functions. Hashing functions may not be considered as broken immediately. Why? Because we can simply increase the bit range and make it difficult for a quantum computer to actually crack the code. Whereas RSA is actually relying on a mathematical problem which can be solved. So there things are different. So there are situations where you can increase the complexity easily, then there is no problem. You can actually rely on those algorithms for some more time. But whereas there are different other problems where you need to completely replace them, then we need to consider better approaches. So that is why we are talking about these ones. So we'll see these families of crypto algorithms one by one. So the first one is the lattice-based crypto system. So these are the lattices. So these structures you would have seen in your chemistry classes or somewhere around in our schools. So they have a regular structure, and these points represents the data points in our lattice. Okay, so just keep that in mind. And so lattices are a set of points in n-dimensional spaces with a periodic structure. So definitely we'll choose something like a periodic structure, and these schemes rely on shortest vector problem. So shortest vector problem could be we actually randomly place something on this lattice anywhere around the lattice. So if I am placing a point over here, okay, and I am actually if I know the lattice, so let's say I place it here. So if I know this lattice, I can easily tell that it is this point that is near to it. But if I do not know this lattice, it is very difficult to predict what is the actual. So this is actually the hardest problem, hard problem here, and the easy problem. If you know the lattice, it is easy to predict which is the nearest one. Whereas if you do not have any information about this lattice, then it is difficult to predict what is the nearest point. So that is the basic problem that we are like, we have factorization problem. These are the problems that we rely on. Now each lattices can be defined using a good base and a bad base. So I'll show you what a good base and a bad base is. So this is same lattice, okay. We can actually represent this lattice using this one, this particular base, and this one as well. So this is almost orthogonal, whereas this is very random. So if I give somebody this particular base, it is very easy for them to regenerate this entire lattice. Whereas if I give this, it is difficult for them to regenerate the entire lattice. So actually we have the good base as the private key and the bad base as the public key. Okay, so if I am Alice, I know what my lattice is, and I know what my private key and public key will be published. So it is easier to generate, actually easier to have encode a message into this using the public key, but to regenerate it, we need to actually reconstruct the lattice. So that is the problem. So for the reconstructing it, the attacker has to find the entire lattice using this bad base, which is actually difficult. So that is how the lattice-based crypto system works. But this actually is a good approach. It is quantum proof. But by listening to it itself, you could have understood that this is actually a relatively easier approach and it could be broken, and it is broken. So that is why when we talk about lattice-based crypto systems, we have to talk about learning with errors. So that is the most practically implemented combination of lattice-based approaches. So we actually start with the equation system. So mostly we take over-defined equation systems. So over-defined equation systems, the problem is that it is difficult to solve, but we actually start with the solution. Okay, so we have a system of equations with a solution, and it will be over-defined. Now what we do is we introduce errors into them. So I introduced errors 1 into this equation, 2 into this particular equation, and no error in this, and 1. So now the problem is, based on these this equation system, it will be very difficult to find x and y. So hope you understood what the concept is. So we started with an equation system which already had a solution. It is very easy. Now I am introducing errors into it, and this is actually equation system which has errors. Now with this equation system alone, it will be very difficult for me to find the x and y values. It is very much clear, right? Now if we add in modularity also into this, this comes within a range, and it again gets difficult. So that is the base of learning with errors. Now we know what is the hard problem and the easiest problem. So now we can design the private key and the public key. So private key is actually the variable values x and y, and public key is actually the equation system. So using this equation system, we cannot definitely find the x and y values. So that is actually the private keys, and the complete equation system is with errors. Now how these two are linked, like lattice and this equation system, so that we are going to see next. So this particular equation system can actually represent a lattice. Okay, so what we'll do is, when we have to place a particular value, let's say 0, okay, so what we will do, we will actually place it with minimal error. So what the let's say I am Alice, I have this equation system. Okay, I will give it to Bob. Now what Bob will do is, he will choose some of these equations, not all of them, some of these equations, and generate a complete equation using that one equation. Like we can simply add it or do any operation and generate one equation based on these equation systems. And to this equation system, if we need to encrypt 0, he will add small error. If we need to encrypt 1, he will add big errors. So it will be like, if it is 0, it will be somewhere here, and if it is 1, it will be somewhere here. So we can actually, and who can actually regenerate it? Only Alice, who has x and y values. If an attacker need to regenerate the value, it will be the attacker needs to solve this equation system with errors and find the x and y values. Only then actually the attacker can regenerate the lattice. So that is the learning with errors. So better versions are definitely available. This is very promising method, but the problem is with lattices is lattices was like if previous year lattice-based approaches was expected to have a certain sort of security or the security level. That level is not being achieved now. Like with advancements, the level of security that a lattice-based approach can give is getting reduced. Like it is not behaving like how we expected. So but this is actually a basic approach, an introduction to lattices. You can actually read about the lattices, and the NTRU system that is there in the NIST, it is actually based on ring learning with errors. So it is a little more advanced effect. So you can, now we have the basic of the lattice learning with errors. So that could be understood easily. So that is about the lattice-based crypto system. Hope it is clear, at least the basics. If you have no questions, I'll move on to the next crypto system. Any questions?
Looks like they're saving them for the end. Uh-oh.
Okay. So hope I made sense. Everything is good. Like if you have any doubts, you can stop me, not a problem. Okay. So next we are moving on to the code-based crypto systems. Code-based crypto systems, again, like all these crypto systems are based on some problem which is actually easy to create but difficult to solve. So these type of functions are called trapdoor functions. So we can say in simple, these are all based on trapdoor functions. So so again, code-based crypto systems is also choosing something which was developed for something else and making it a trapdoor. That is how we go. Okay, so code-based crypto systems is actually something which was designed rely on error correcting code. Error correcting code, no, we know that it is something entirely different. It was actually designed to correct the errors in the data transmission. Like if we send, let's say 101, okay, when the recipient is receiving 111, there should be some method to detect that the middle one is actually having an error. So there are two basic approaches. One is detection and one is correction. So detection, it is easier to add parity checks. For correction, the easiest approach is resending it multiple times. So based on the maximum probability, we can choose the element that is there. So this is actually basic error correcting code. Now see, sending the entire message multiple times is not a very good idea. So we have the linear error correction codes, which is actually an improved approach where we actually basically matrix multiplication it is. We actually multiply with the matrix, we generate a value, we do the inverse. So it is as simple as that. So we have the data, when we have error correcting code matrix and we generate a value. Now the important thing to note here is if we have, let's say 4-bit message, okay, now I'm multiplying it with the error correcting code matrix and I'm getting 8 matrix. So it depends upon the size of the error correcting code matrix I'm choosing. So the result is actually 8 bits. So for actually the 4-bit input, I have got 8-bit output. So now my overhead, that is the additional bits that I have added is 4. Now when I add additional 4 bits, I can actually correct 2-bit errors. So that is the basic concept in linear error correction code. When you add an n-bit overhead, you can actually correct n by 2 errors. Okay, so that is the important thing you have to remember. It is simply based on the matrix multiplication and inversing it. And when you add actually n bit into the add n bits into the original message, you can actually correct n by 2 errors. Okay. Now this again, if you simply choose any random matrix, it is not very easy to inverse it. We know that, right? Matrix multiplications is not very easy for every matrices that we choose. So we actually have set of good matrices which actually efficiently allow the error correction. So they are classes of good matrices which allow for efficient error correction, and these good matrices are being developed and identified. So it is already there. We have to choose such a good matrix here. Okay. Now we have a good matrix. So what is the advantage here? If we have a good matrix, error correction is very easy. Okay, so we have chosen a good matrix. Now we have an easy step. Now we have to design a difficult step. So now what we are going to do is, we'll take this good matrix, we can actually convert it into bad matrix. Bad matrix is nothing but a matrix with which you error correction is difficult. Okay, so we can actually convert a good matrix into a bad matrix using blend matrices. So this is actually matrix properties. So when we multiply this good matrix using a blend matrix, it is converted into bad matrix, with which we cannot actually easily perform this and do error correction. Now we have an easy problem and a difficult problem, and have a problem, have a value with which we cannot easily come back to the starting state also. Now we have designed our public key private key system. So our private key is actually the combination of good matrix and the blend, and our public key is actually the bad matrix that we have generated. So we know using the bad matrix, and so attacker will definitely have only the bad matrix. Using the bad matrix, error correction is very difficult. Okay, so and using this particular combination, error correction is very easy. So now what the sender will do is, he will take the plain text and use into this bad matrix. Actually, he will like do the multiplication and add errors. Okay, so now the plain text and the bad matrix is multiplied. So bad matrix is the combination of good matrix and the blend matrix, and errors is introduced. Now if we know the good matrix, we can easily find the errors. So any person with this combination, it is very easy to find these errors and regenerate the plain text. But for someone with only the bad matrix, it is very difficult to regenerate the plain text from these errors. So what is traveling through the network is actually a message encoded with the bad matrix and errors into that. So the message with the errors is traveling. So we cannot actually identify which is the original message and which is the errored message. So that is the advantage of it. And in real implementations, we will take, let's say for a 5413 bit message, we actually converted into 6960 bit, which has an overhead of 1547 bits, with which we can correct actually byte to 773 errors. So we definitely have an option to include 773 errors into the message. Okay, so if we take this many bit message, we actually can introduce 773 errors. It is a huge number compared to this bit message. So when we introduce so many errors, but it is not even required to introduce so many errors. By simply introducing 200 bit errors or less than that, we can achieve the level of security that we need. So that is code-based crypto system. So code-based crypto system is based on error correction matrices. We will take a error correction system that was working properly. We added errors into it deliberately, and we will make the a person who has the good metrics to, they can easily solve it, but the attacker cannot actually remove the errors. That is the basic concept here. So, and Meklil's crypto system is actually one of the examples for code-based crypto systems. I hope that is clear.
This is John. Can I ask a question?
Yeah.
Are there any problems with this system if the errors are introduced with some sort of pattern? Would that make it easier to kind of break the encryption?
If errors are introduced with patterns also, yeah, definitely there is different attacks to these crypto systems, which are actually again classified ones. Pattern based, yeah, when we introduce a pattern based error system, like if we introduce like every alternate numbers, that is definitely a problem. So if that is known to the attacker, definitely they can find some method to basically attack it. So definitely we are not going to introduce errors in a specific pattern. We'll actually have some random method of inserting it. So such attacks are also defined based on these code-based crypto system. Definitely pattern is not a good idea. Following a pattern is not a good idea, and if the attacker can get the pattern, it is definitely a problem.
Can I also ask a question?
Yeah.
What happens if there are errors in transmission?
See, that is why we keep almost this overhead. We have we are introducing only 200 bit errors. So so we have some like big gap again. So even if the errors comes in with the transmission, it will be rectified.
Okay. Okay.
Yeah. So now
yeah, I have a question too.
Yeah.
Yeah, so like this is basically based upon the fact that the matrix multiplication and inverse stuffs are like difficult to compute, and thus it is safe. But for like a quantum computer, it will not be that difficult, right?
Yeah, that is where we are coming at. Like when we take a small number, it will be like looking very easy. But if we are dealing with very huge matrices, this won't be like it is a trapdoor one. Like we have a generic pattern and which is very random. So see, quantum computers basically actually work on like if you have a problem and one solution is there. So here the problem is that we have a series of number where in multiple locations we have a correction. So what quantum computer will have to do is it has to fix one location, work on the next location, again fix that, work on the next location. So things get difficult. Did you understand?
Yes, yes, yeah. Thank you.
So, real world implementations, it is not very small numbers. That is the problem with code-based crypto systems as well. So to have it practically implemented, the number that we require to achieve the desired security is very huge. So that is where the researchers are working on right now. Codebase is actually a good one, but we cannot actually implement it properly. See, to achieve the desired from 2 KB, we are going to 1 MB size of key. So that is not a good thing. So real world implementations gets difficult. So we can actually work on the private key and the public key compression techniques and make the security level the same. We can actually use different codes, which there are multiple error correcting codes. We can actually maybe use some of them, and specific coding techniques could be introduced apart from these introducing errors, like the way we are introducing errors. So modifications can be brought in to increase the efficiency. So now the problem is we need to store this very huge number size plain text, and I mean the private key and the public key, and it is very huge for the computational requirements or the resources we have today. So that is the problem with code-based crypto systems. So hope this is clear. We can move on to the next one. Yeah. So next we have the hash-based crypto systems. So hash-based crypto systems is basically relying on the, as name suggests, it is based on the hash functions. Okay. So this is actually the most theoretically secure ones, which we are very much using today. We are extending it to the post-quantum cryptographic scheme, but they are used for signing, not for encryption. The other two methods we have been discussing, it is for encrypting. Here we are basically using it for signing. So let's say I want to say yes and no to someone. Okay. So I'm basically writing an agreement and I want to share yes or no. So what I will do is I will actually send I will actually generate a random number, two random numbers, one actually representing yes and the other representing no. And I will actually convert it, the hash values of these random numbers, one represent yes and the other no. And I will actually convert their hash values, and this hash value will be shared with the person, okay, initially. Now, when I need to say yes, what I will do is, I will take the actual random number and share it with the person. So this person will keep that random, this particular random number, convert it into the hash value and match it. So what will happen? It will actually find one of the matching hash values, and that will be the my message to that person. So here the problem is actually the private key was the actual numbers that I used. Okay. Now for the system to work, I have to actually share my random number as such, the private number as such, you can see. So this will actually work only once. So for the next time I have to tell yes and no to the same person or a different person, I will actually have to choose a different random number representing my yes and no. That is the problem with this. Hope it is clear. Any doubts? Okay, So this is actually verifying the actual message that I wanted to send and ensuring that that is, so nobody will actually tell the no, I have told no in the first place. So that is the simple approach. It is basically for signing. Now, only problem for this is we can use it only once. And so definitely it has a generally poor performance. It is not a very good competitor in signing approaches, because for every single, like let's say for example blockchain itself, like for every single transaction, if you have to generate new, it is not a good idea at all. So that is not a good way of signing or something like that. So but definitely a lot of researchers are working on it. They are coming up with methods which can actually reuse it, better performance. So many algorithms are coming in, but basic hash-based crypto systems are working on this approach, but there are modifications in it. You can definitely read about them. That is the basics of hash-based crypto system. Okay, so I hope I can move on to the next one. Next is multivariate crypto system. So multivariate crypto systems, by the name itself, it is very clear. It has a system of equations which is having multiple variables. Now what we do is we actually choose which demonstrate NP hard and NP complete issue trait actually. One of the examples is ladder problem. So multivariate equation systems which actually demonstrate NP hard or NP complete problems is actually chosen. And then we build on it. So use of square matrices with random quadratic polynomials is an example. So this is actually an algorithm. I'm not getting into it so many details. Hidden field equations. All these are examples of such multivariate equations. See, there are specific sort of sets of problems which actually demonstrate this property. We will actually choose them, and we will make actually the crypto system built on it. So that is how it works. And here the problem is the decryption speed and the key size. For almost all of the post-quantum cryptographic schemes, the problem is we can actually, for Lattice also, we can actually encrypt only one bit at a time. Code-based also, we had a big, huge matrix. Hash also, we can use the entire scheme only for once. Multivariate systems also, we have a very slow decryption speed and high key size to achieve the required security. So these are the problems with the multivariate crypto systems. So definitely we can bring in solutions on these areas. You can, if you are interested in working on them, you can search on like how we can actually reduce the decryption speed and how we can work on the key size, like compressing them if it is possible, and still maintain the NP hard problem of them. So that is it is as simple as that. It is based on equation systems with multiple variables. So that itself brings in the complexity. Now we actually choose in the set of equations that demonstrate the NP hard and NP complete problem. So that is multivariate crypto systems. So I hope it is clear. So we'll have to, this is like, once we get into this, this is very much mathematically complex. So if we go inside, we will not be able to like give a brief on that. It is definitely, it is mathematically indexed. I will not say mathematically complex. It is very beautiful mathematical solutions that is there inside. So if it is very beautiful, actually, you can, once you go inside, you can definitely see how that these actually demonstrate the property that we require. Okay. I hope that is clear. Can we move on? Okay, so next we have other crypto systems, that is isogeny based non-commutative crypto systems. Isogeny based crypto system is actually a very good upcoming and very good hopeful solution actually. What is the difference from like elliptic curves crypto systems that we have today in isogeny based crypto system is that in elliptic curve crypto system, we basically choose elliptic curve and we actually use the elliptic curve properties to develop the crypto system. Now in isogeny based crypto system, we actually choose elliptic curves with certain properties. Like it has around 12 to 20 properties, which is again very which has certain mathematical properties on the elliptic curve. There is restriction on choosing the elliptic curve. If we fail in choosing that elliptic curve wrong, if we choose that elliptic curve wrong, it is same as our old elliptic curve cryptography. There is no difference. So in isogeny-based crypto system, we actually go for elliptic curves which has these specific properties and build the crypto system on them. It is as simple as that. So those who are interested, you can go and read about like elliptic curves crypto system, how it worked. Like there are around 5 to 6 principles of it, like the product of any point, it is actually how it is coinciding on the elliptic curve. That is one of the like if you take the power of any point on the elliptic curve, it will be another point on the elliptic curve. That is one basic principle of the elliptic curve working. So similarly, you take an elliptic curve with even more complex properties. So what will happen is it is more restricted. It will not be very easy to predict the points. So that is how the isogeny-based crypto systems work, and they are enhanced to withstand the quantum attack. We do the analysis on those elliptic curves and analyze them, and we choose them which can actually withstand the quantum attacks. That is how isogeny-based crypto systems work. If we go wrong with the choosing of elliptic curves, it is as simple as the old elliptic curve cryptography. There won't be any difference. So the security lies in choosing the elliptic curve that we are going to use. That is as simple as that. And its properties. So and this is actually one of the main approaches which could be for the blockchain. A lot of people are working on it for isogeny-based crypto systems to be introduced in the blockchain, because we know like currently everything is based on elliptic curve, so it is actually sort of easy to like transition also using this approach. So that is why it could be, we cannot predict because all the analysis is going on. So it could be one of the promising solutions for blockchain approaches, etc. Next is non-commutative crypto system. So I will actually explain it like this. We have a Rubik's cube. So that is how in many of the lectures it is explained. We have a Rubik's cube. Okay. So we have a series of transitions, like I rotated it like this and so many things. Then we have another sequence B. Okay. So I can actually find a pattern like this. Okay. So if I will do one operation, I'll do some modification on this particular sequence result, then I'll get B. See, you have a Rubik's cube. Okay. So I am doing some rotations on it and I am having a state. Okay. Now I have another Rubik's cube which I have on some state. Now if I do some operation on the first Rubik's cube, and I can actually make this Rubik's cube go into that state. So I can find a X, definitely it is possible. So I can find a X actually applied on A will generate this B state. Okay, but this is actually a very good concept, but there are no more algorithms actually in NIST post-quantum race right now because of its practical complexities and different other reasons. Maybe in the future somebody can come up with a very good example, like so what this particular equation combination could be very strong, and this can actually help us in generating the crypto systems. So that is not crypto systems. Many people are working on it, but right now it is not a very not in the limelight because almost all the algorithms under this method is out of the race, out of the competition. Next, we have hybrid approaches, which is actually not in the NIST competition, but this is actually a practical solution for the immediate future. Why? Because immediately changing all of the infrastructure, all of the algorithm schemes that we have today, will be difficult. We definitely need we cannot actually transition from here to here. We actually have to have a gradual transition. So immediately there is a state where, like this year beginning, RSAs were safe until like 10 to 15 years. But now when we look at it, the prediction of RSA being safe till 2025 is also like confusing, because there could be at least theoretical methods of solving a 2048 bit RSA. At least theoretical. I'm not telling practically, but theoretical approaches could be designed which can actually be applied by someone. So we have an immediate requirement for transition. So we actually could basically use some of the existing classical crypto systems that we have and merge it with the post-quantum crypto systems and increase the security. So this is actually one immediate practical approach that we can do. So that crypto systems is also there. So what we are trying to achieve using these post-quantum cryptographic system is, we have to persist ourselves from classical attacks, quantum attacks, and these post-quantum schemes also come with sort of attacks. Okay, so lattice cryptographic systems, as one of the sirs have asked, like when we have code-based crypto system, it has its own vulnerabilities. When we go for lattice, it has its own vulnerabilities. So we need to protect these crypto systems from those vulnerabilities as well as the classical attacks. So that is what we are targeting at. So we have to look into, so when we are actually choosing a solution for our industry or a practical application, we actually have to focus on these three things from now on. Like we have to make sure that it is securing against all the known classical attacks, because there are quantum schemes which is actually resistant to quantum computers, but classical computers can break them. So that such sort of algorithms are also there. So we need to look into classical attacks, quantum attacks, and whichever solution we are implementing, the vulnerabilities that it has. So many evaluations are being done at the industry and academia, and immediate changes definitely required. Now, there are a lot of studies going on. So one of the major like hitting point for us was like when NIST called for a post-quantum standardization competition. That is when actually it got very serious also, I believe, because we came to know, yeah, their standards is not secure. We are having to have a transition of the standards that we are using today. It is not a small thing. It is predicted to be the biggest technological transition we ever had. Like almost for 20 years, when RSA was developed, it was a big revolutionary. It was not expected to break for so many years. But all our predictions, all our assumptions are wrong now. We are actually trying for schemes that could replace RSA or even improve RSA, something like that. So this was actually one of the awakening point for many organizations and many institutes. Then we have, it is not only the NIST post-quantum standardization, there are many other projects that is working towards it. So these are some of the post-quantum standardization and evolution projects. There are many projects that is coming up as well. This is the ones like caught my attention, and ones that I follow also. Again, let's look a little into the NIST post-quantum standardization. So first call was around 2017, and first round was announced in December 2017 with 64 candidates, and second round around 2019, and like many were eliminated. You can see the problem with post-quantum cryptographic schemes is that many of the suggested ones were broken. Like the computational security in many of these competitors were actually broken, and we could actually bring in only 26 out of them, and some have withdrawn also. So again, the third round, which happened very recently, 7 candidates was finalized, and we have alternate also. They have kept 8 alternate candidates for possibly could be the finalist also. and for different applications. See, some of these standards may fit, some of the algorithms may fit in for certain applications, whereas others will fit on different applications. So that is why they have considered it like this. Then they are expecting to draft the standard by 2022 and 2023. And there are a lot of articles coming around recently, like this could be a very long time. We cannot wait till then, but hopefully we will see how NIST responds to it. Now, the NIST post-quantum standardization basically is looking for algorithms in these three approaches. One is for signing, one is for key encapsulation, that is sharing the key, and is the general encryption, that is encrypting the data. So these are the three approaches, and these two can be combined actually. We can actually send the key encapsulation also and the key encryption also in the same way. So this is actually the summary. We had for so many people in the initial round. 45 was there in total, but later it got reduced, and now we have 4 in PKE scheme, that is the public key and the key encapsulation, and in signature we currently have 3 and the total 7 and 8. So this is the summary of NIST post-quantum standardization, and hopefully we will have standards from here. And actually NIST is open for modifications on these also, so definitely some approaches should come in, like on these algorithms modification or anything like that. So then last 7 finalists. Now we know what is lattice-based approach, code-based approach and all. So under last 7 finalists, you can see that we have only lattice and code-based approach. We do not have a multivariate based system or something like that. So in signature based, we have lattice-based and multivariate algorithm, which is there. So we have talked about Mathews, and NTRU is actually a ring-based learning with errors. So yeah, it's very interesting. Like you can actually go into one by one. So that is so we can say, look, simply by looking at it, we can say that lattice-based approach is a very good competitor. Like we have in here also we have 3, and here we have 2. So this is actually a very good approach, but that is the problem. Like recently we are seeing that the amount of security it was expected to give us decreasing with time. Like as the computational power increases, that problem is also there. So you'll have to analyze, have a good analysis on these systems, how it can respond on these different issues that we are facing, on these different attacks and the computational advancements that we are getting. Next, the alternate schemes are these one. The lattice, we have code-based approach, and we have a elliptical isogeny here. It has come in. So this is actually a good sign. So again, we have for signature, we have the hash base, and we have a zero knowledge protocol also. And another important thing, like a homomorphic encryption, a lattice-based approach was actually a starting point for homomorphic encryption as well, which was actually a problem for so long. That is also there. So a lot of interesting things are happening here. So these are also promising. It is not that those were eliminated were not promising, but this is what the NIST standardization, it was evaluating based on actually 5 security levels were there. Then we told 3 operations, then performance. We are looking for lightweight devices. That is very important. Performance on the lightweight devices. That is one of the biggest considerations. So based on that, these are the 8 alternative candidates, and these are the 7 finalists. So yeah, that's it. So I hope it was useful. Sorry, I can't hear you.
My backup system worked too well. So that, I think that was a great like overview of everything, and there's countless number of hours required now for me to dig into each one of those items. So thank you for all the homework that you've created for me. I've been digging into the quantum space, and I've learned some interesting things as I go into cryptography and all that. I'm familiar with the AES and DES and all the other S's out there, but I find this a very fascinating field that I think we all need to really become more familiar with if we're going to call ourselves technologists, because this is definitely going to be front and center in the years to come, no doubt, especially if you're in the quantum community, but even just back in the classical as well. So does anybody have any specific questions while we're here? George, you type something in. I hope your microphone. Where's George? Yeah.
Hi, is that working?
It's working.
Yeah, I was curious about isogeny-based elliptic curve. That one is new to me. With respect to dual elliptic curve encryption, there was concerns about backdoors. And actually, I'm curious about any of these methods, whether that is a concern. That the person supplying an elliptic curve could keep a secret backdoor.
That is actually depends upon the implementation. So that is a different sort of security issue as such. So like I have not very much digged into that, but yeah, definitely implementational side issues could be there. But I have not digged into like how it is affecting the isogeny based elliptic curve systems, like how it is replicated and how intensified that issue is with the isogeny based systems.
Thank you, and thank you in general for an excellent overview.
Yeah, this is actually sort of skeleton. We have to go to each and every pieces. Yeah, it is like one box. You have to open the other box and then go inside. So yeah, that was my target actually. Because to collect everything and to like where to start with. Yeah, that is actually my target. Yeah, I definitely know this is nothing, only not even like scratching the surface. Like we have to definitely dig in more, but it is like a starting point. Such information really helped me. That is why I shared it. Like that is how Daryl actually called me also. So yeah.
The information on the NIST and other programs was mostly new to me. That was very helpful.
Yeah, thank you.
Yeah, it sounds like your experience what I experienced for seeing the talk. It's just, you can go to the NIST website and it's just like, yeah, I'm deer and, I like digging into stuff, but that's not pleasant. This really gives you kind of a good start, the lattice techniques and stuff like that. It's like I said, there's so much, there's so much homework behind this, George.
Oh yeah, I'm still struggling with Silverman and Tate rational points on elliptic curves. I'll maybe never get to the bottom of it.
Yeah, I mean it's almost a rabbit hole as deep as quantum.
Yeah, that was definitely a one big session like possibility.
Yeah. I think what I find most exciting and new about quantum is the possibility of true random streams of bits.
Yeah. Yeah. As Mahima's going through the whole time, with the post-quantum cryptography, as she's talking, I'm sitting there looking at, one-time pads, QKD, and we're done.
Yeah.
But You know, in practice, that I'm having that discussion. It sounds like you're having it within yourself too. But in practice, you know, that may not be practical in every use case out there, you know?
No, certainly not.
I mean,
One-time CADs are very expensive. The key is as long as the message.
yeah. Well, I mean, with IBM and Cambridge coming out with, you know, random as a service, it's a little closer to practice. But then, you know, I started thinking, well, maybe that's only good for data in transit. You know, data at rest, you're kind of, we need stuff like this, I think.
Yeah.
At least that's my thinking. Mahima, you got any thoughts on, you know, I mean, I think to this audience, it's fair to say, you know, everything looks like a quantum computer could solve it, but we may be reaching too far on that. You know, computationally secure cryptography is not going to go away. I think that would be my
that is actually the immediate way to approach because unconditional security that the quantum cryptographic systems is going. It is actually, yes, very costly, and it demands for a complete infrastructure and the protocol change. So it is very costly immediately. Maybe gradually, like with quantum networks and all coming in and commercialization of quantum networks, maybe it could be a revolution. Like it can be linked with the quantum networks actually. So like quantum networks is actually long way ahead. So yeah.
But you know, I think I paid $200 for one of these around 12 years ago. So, you know, expensive, I don't know. That's just a temporary problem.
Right now it is. Yeah. Like, but if these are the immediate way we can address the problem. This is the best immediate, and it is having a computational provability also. Like until people like develop some algorithm again to solve these, until then we are safe. So
that's our job. That's our job in the community. We're going to put Peter Shor out of business. Somebody in the community out here, some 12-year-old or some 60-year-old is gonna you know, put Mr. Shor, Professor Shor out of business. We're going to find something better. I know we will.
Finding the right combination of near-term hardware and your choice of these different crypto approaches will be a real challenge.
Bring it on, man. Bring it on.
Yeah, that's a fun challenge.
Anybody else? Krishna, I heard you earlier. Barry, you're awful quiet today. Are you okay? Others? John? I think I heard from you earlier, John. But...
I'm okay, but I'm so busy that I've got to listen with one ear and do other things with the other ear.
I hate that mode. I was at the beginning of the talk. I'm stuck in a standards meeting that's been going on for 4 hours. But you got to kind of listen. It's tough. It's tough. Sarita, anybody else? All right, Mahima. Oh, wait a minute. Something just came in. Sarita just. So which protocol it will use? What will be impact on performance with quantum encryption and decryption? Because in classic encryption and decryption, many times due to performance degradation, business shies away from encryption. So let me see. Can you see that in the chat, Mahita? Trying to parse out. You know, business still shies away from encryption. I personally, you notice Quantumapalooza still is not HTTPS.
Yeah.
I understand the technology and all that, but I'm not touching my systems because there's just too much risk. And if I don't have to protect anything, I'm not doing it. So I could see that attitude, you know.
Yeah, that is definitely a problem, like educating the people that there is actually a need of shift is actually a big challenge. Um, uh, because like nobody is going to immediately trust, like within the community we can understand the intensity, like no, if you actually go to the business, they are so happy with their like security systems. They are able to at least like they have spent a lot of money into it already. So like changing the entire infrastructure could be a like replacing the server room with photon transmission transmitters and generators and all will be like it is like a big education process, like we'll have to learn it hard way maybe.
Yeah.
Yeah.
I always think in this part, I always think of IPv6.
Yeah.
You know, that's my bumper sticker. We've been
So,
trying to gravitate, I guess we're up to 20 years now.
yeah,
And we're finding Band-Aids around, you know, going to IPv6, but eventually those Band-Aids aren't going to work anymore. Anyway, I'm a late adopter. Like I said, I'm still working on HTTPS for my sites. All right, anybody else? Thank you, Sarita. Krishna, Daniel, Mark. The left ear of Barry, hello. Anyway, all right.
I'm good.
Thanks. just doing a wellness check, that's all.
Yep.
All right, Mahima, thank you very much. Thanks.
Yeah,
Oh
thank
yeah,
you.
got the clap from Daniel, the applause from Daniel. I'm going to give
Thank you so much
I,
actually to be able to talk to you all. It's a wonderful opportunity to be able to talk to people in this community, like so experienced people. Yeah, it could actually be a blessing. Yeah. So thank you so much.
Thank you. We're blessed to have you here. And let's keep in mind, you know, when this comes out for the next round, why don't you drop by again?
Yeah, sure. And yeah, you can always reach out to me also. Like I'm into this work since I'm a PhD student right now, like everything into this. So I'm also learning. So yeah.
We all are. How much
Yes.
more of your PhD, or how far along are you with that project?
Right now I'm first year. Like I just completed my
Oh.
coursework.
All right. Well, congratulations.
Yeah, thank you.
Good luck on the journey.
Yeah, thank you so much.
So much more to go. But you
Yeah.
know what? You know what? When you finally defend your thesis and all that goodness, that's just the beginning of the journey. Trust me.
Yeah, true.
Hopefully, anyway.
Yeah.
All right.
Thanks for the support, and yeah, I'm looking for more associations and all. Thank
All
you
right.
so much. Yeah.
Come visit anytime.
Yeah, thank you.
See ya. All right, folks.
Thank
Thanks.
you all. Thank you all for your time.
Bye-bye, everybody.
All right. Thank you so much.
Yeah, thank you.
You.